Suppose all of the nuance and complexity of political conflict could be represented with a single line. That line might represent conflict between the political left and the political right common to many modern states. And if we can represent that political conflict with this line, then we can also place every politician on that same line. We might have a legislature with 3 politicians, one who takes the position to the left, one who takes the position to the right, and one who takes the position in the center. We can represent those 3 politicians by these 3 points on this line. The line could also represent the spectrum from liberal to conservative, more familiar for an audience from the United States, or a specific policy, like the spectrum from being pro-choice to pro-life. When we think about politics in this way, in the way that many political scientists think about politics, we can begin to derive general theories of political dynamics and start to understand systematically how politics works. This video is an introduction to the spatial model of politics. By starting with the basic building blocks of the model, we will begin to understand how to use the spatial model to analyze political choices and political outcomes, and ultimately derive one of the most influential theories in political science, the median voter theorem. For the rest of this video, the line will represent minimum wage policy. Now the center politician's position is much more concrete. They think the minimum wage should be exactly $5. We want a way to account for this politician's preferences over every possible minimum wage, so we can compare different policies from their perspective. We'll do this by creating a utility function for them. A utility function is a function that takes a policy as an input, in this case a minimum wage, and outputs the utility a politician derives from that policy. We borrow this term utility from economics, and it means something like satisfaction, happiness, or general goodness. We'll assume a politician's utility function, labeled here as u of x, is single-peaked and symmetrical. This means that there's a single policy that gives that politician the most utility possible, and that politician's utility decreases equally as policies begin to deviate from that maximum in either direction. We can represent this utility function as any single-peaked and symmetric function, but we typically represent it as a quadratic function, a parabola. A parabola is a symmetric function. You can see as policy moves right and left, the utility the politician derives from that policy decreases at the same rate in either direction. It is also single-peaked. It has a single maximum, in this case when the minimum wage is exactly $5. Let's label the legislator with this utility function A and represent them as a point on the minimum wage line that maxes their utility. We'll call that point their ideal point. We can imagine a legislator with an ideal point anywhere on the spectrum. Maybe they want a lower minimum wage, maybe they want a higher minimum wage, but let's put them back at $5 for the rest of this analysis. When we draw back in this legislator's utility function, we can begin to see how they might make decisions when faced with real alternatives between different minimum wage policies. In legislative choice settings, when legislators are tasked with making a decision, with voting yes or no on a policy, there's always some existing policy, some status quo that we'll label SQ, that represents the current policy on the books. There's also some proposed policy, labeled here as X1, that is pitted against the status quo. In this case, legislator A is making a choice between keeping the status quo minimum wage at $2.50 or updating the minimum wage to $6. To determine how legislator A will vote, we just need to compare the utility that legislator derives from the status quo and from the proposal and see which one is higher. Here we can see that legislator A derives more utility from the proposed policy of $6 than the status quo at $2.50. Therefore, they'll vote for the proposed policy. Because the utility function is single-peaked and symmetric, asking which policy gives more utility to the legislator is the same as asking which policy is closer in space to the legislator's ideal point. From these building blocks, we can begin to model policy outputs from full legislatures using majority rule. Suppose we have a legislature with 5 legislators, A, B, C, D, and E, and suppose they're voting between a status quo policy of a $3 minimum wage and a proposed policy of $4. We can go legislator by legislator and see how each of them will vote, and determine which policy, the status quo or the proposal, garners a majority vote. We can see that A and B are closer to the status quo, but that C, D, and E are closer to the proposed policy. Therefore, C, D, and E will vote for the proposed policy, forming a majority and passing it. We can pick a new status quo and proposed policy and see what would happen. A will vote for the status quo, but B, C, D, and E will vote for the proposed policy of a $3 minimum wage. B, C, D, and E will form a majority and pass the policy. We can move them again and do the same exercise. Now, A, B, and C vote for the proposed policy, but D and E vote to keep the status quo. So A, B, and C form a majority and pass the policy. You'll notice that legislator C is in every winning coalition. Legislator C is also the median legislator. If you line all the legislators up from left to right, C is exactly in the middle. This turns out not to be a coincidence. The median legislator is always in the winning coalition. And what's more, the policy that will eventually come out of a legislature when conflict is organized along a line like this is always exactly the median's ideal point. We call this the median voter theorem. In order to understand why the median voter theorem works, we need to take some intermediary steps first. First, we want to find every policy that a legislator prefers to the status quo. We did this for some specific examples before, but now we want to find every single policy that the legislator prefers. We can do this by plotting some random policies and turning them blue if the legislator will vote for that policy, and turning them red if they'll vote to keep the status quo. As you can see, policies that are closer to the legislator than the status quo are those that the legislator votes to pass, and those that are farther from the status quo than the legislator are those that fail. We can do this for hundreds of policies and start to see the range of policies the legislator prefers to the status quo. We can already start to see the shape coming into view. Because the legislator votes yes on policies only that are closer to its ideal point than the status quo, policies that are very far from the legislator are those that they vote no on, represented by red. We've now simulated enough decisions, and we can see the range of policies the legislator prefers. Clearly, they prefer policies that are to the right of the status quo up until their ideal point, because this represents increasing the minimum wage closer to their ideal point. But they also prefer policies that are that same distance on the other side of their ideal point. For example, $6 is closer to $5 than $2 is. We'll call this full range of policies that a legislator prefers to the status quo their preferred two-set. We can see how the preferred two-set changes as the status quo changes and the legislator's ideal point changes. It gets bigger when the status quo is farther from the legislator's ideal point, because there's more policies that the legislator likes more than the status quo. And it gets smaller when the status quo is closer to the legislator's ideal point, because there's fewer policies that the legislator likes more than the status quo. With this definition in hand, we can go back to our model of a full legislature of 5 legislators, A through E. We can build up the preferred two-set for all 5 legislators and determine all of the policies that win using majority rule. The set of policies that can win using majority rule is the set of policies that a majority of legislators prefers to the status quo. Another way of saying that is that the set of policies that can win is equal to the overlap of a majority of preferred two sets. In this case, with 5 legislators, a majority is 3, so the overlap of 3 preferred two sets is the set of policies that can win. And we call that set the win set. It's the set of all policies that can beat the status quo. We can move the status quo around and see what happens to both the preferred two sets for each legislator and the overall win set. In every case, the win set ends up being exactly the median legislator's preferred two set. This is extremely useful analytically because it means that we can simplify political problems in legislatures to just a question of what the median prefers. regardless of whether we have 5 legislators, like some small city councils, or 435, like the US House of Representatives. To get to the final step of the median voter theorem, showing that the policy output of a legislature is exactly the median's ideal point, let's relabel legislator C as legislator M, the median. Now, let's model a series of votes in this legislature. Suppose that a bill is before this legislature that would move the status quo policy somewhere within the win set, meaning that the median is going to vote yes on that policy and the policy will pass. When that policy passes, it becomes the new status quo. Let's repeat this process until we find a policy that cannot be beaten, a policy that has no win set. To do this, we'll draw in a new win set for the new status quo, pick a new policy within that win set, make that the status quo, draw the win set for that policy, and continue until we find a policy with no win set. This process reveals that the one policy that has no win set is the policy that's exactly at the median's ideal point. We'll call that policy the equilibrium policy and label it X star. This means that any status quo policy will eventually become the median's ideal point through a series of majority votes. This is the median voter theorem. The spatial model of politics is an extremely flexible model of political dynamics and is a workhorse for many political economic models of how politics works. We can use the spatial model to understand the effects of the filibuster, of the presidential veto, of judicial review of legislative statutes. We can even use it to analyze elections. The simplicity of the model with one line, one dimension, is useful for analytical traction, but clearly misses a lot of the nuance of politics. The next video will explore the spatial model of politics in 2 dimensions, where there are 2 different dimensions of conflict.